I've been building data science infrastructure for well over a decade now. Most recently, I was at Netflix building ML infrastructure to power all of Netflix's ML efforts, whether it's figuring out what to recommend when you log into Netflix.com or recommending content execs at Netflix what content they should be buying or producing to maximize Netflix's business revenues. We were solving problems like figuring out when somebody is online, they're browsing Facebook or they're on NewYorkTimes.com, what ads to show them so that they'll go ahead and subscribe for the service. As well as at the same time, when somebody is walking on the streets and they look up and they see a billboard, which Netflix show should be featured more prominently on it so that we can drive higher and higher signups within a specific geographical area. For those of you who work at or have worked at medium and large size enterprises, you would recognize that there are many business activities, many business processes that are ripe for significant efficiency gains if machine learning was introduced into them. But then the biggest barrier is that whenever any organization thinks about investing in ML, there's a large upfront cost that needs to be paid to get any level of success. There are plenty of statistics that go around talking about how few percentage of projects ever make their way into production. And it's important before we sort of like start getting down into building tooling in this space to really understand why that might be the reason and how can tooling actually go out and fix that. My biggest take from my stint at Netflix was that building human friendly tools, building productivity centric tools is the key to fixing this issue. If you look at many of the recent trends, and when I say recent, this recency stretches for the last 1 decade, even more than that, there have been a steady supply of great technical advancements. On the machine learning front, every single week we hear about newer and newer innovations. On the compute side of the house, on the infrastructure side of the house, there have been massive advancements that have been made. If you look at the early days of the cloud, when AWS just started, a general purpose EC2 instance would have a couple of gigs of RAM. These days, you can get a terabyte of RAM quite easily from AWS. And it doesn't matter if you are a big behemoth like Netflix or if you are a very small two-person startup, you have access to pretty much the same kind of infrastructure as well. So there has been a steady increase, might I say, an exponential increase in technical capabilities that are available to us. There have been an even impressive increase in the desire to take these technical capabilities and introduce these in organizations to make organizations better across all dimensions. But then the big missing gap there is all about productivity, right? I mean, you can go out and you can get sort of like the most exotic of GPU instances from your cloud providers, but then it'll still take a lot of time and effort to figure out how to eke out maximum benefit from those. When it comes to even executing on a project that involves, let's say, predicting what probability any specific customer of the service has in terms of their churning away, there are a lot of questions that organizations need to solve, right? Like, how do we get access to the data? Is this data something that they are legally, uh, is this data that they are something that's legally allowed for them to process on? How do people run large scale compute? How do people take these models and deploy these into production? What is that definition of production? How do we think about managing and operating these systems at a large scale? If we have many of these projects, and if you have to deal with the diversity of many different machine learning applications, how do we deal with that kind of entropy as well? And all of these introduces a significant barrier to entry. And our goal was that, okay, internally at Netflix, can we make it super simple and straightforward for any data scientist, anybody who is interested in introducing machine learning into their projects, dead simple. And let's talk about how we went about doing that. Let's take the example of, let's say, a hypothetical data scientist, and we can imagine that, this data scientist of ours, they are focused on solving, let's say, our pet problem. Let's identify whether a user is at a risk of churning away over any given time duration. And of course, if we are able to sort of like predict this with any given amount of accuracy, then we can take some corrective actions. We can shower them with discounts. We can provide them higher level of service. We can make sure that their phone gets picked up ahead of line compared to any other customer, so that the probability of them actually churning away goes down. Now, this data scientist of ours, of course, they need to do some data analysis. They need to do some models. That activity needs to happen somewhere. More often than not, that happens to be a laptop. In organizations that are sensitive about data security, that laptop may live in the cloud. It could be a notebook instance running on some VM. And the first question that a data scientist needs to answer is that, okay, what data can I access? What data exists in the first place? How can I efficiently access this data, right? And once you have access to this data, then of course, you can do some data exploration, and you can sort of like, start generating certain hypotheses around what kind of models you may want to build. Then the next barrier that comes up is that, okay, of course, like it's all good and fine if the data fits in that instance. What happens if it does? How do you get access to a larger machine in the cloud? What happens if you want to train a model that requires GPUs? How do you get access to a GPU machine? What happens if you want to train many different models in parallel? How do you get access to many machines? And how do you sort of like manage that complexity? How do you take the code that you have written, let's say in your notebook, move it into the cloud, ensure that that cloud instance that you just spun up, that also has secure access to this data source. And then you're able to look at all the job logs, you're able to triage any issues, debug any failures without really relying on external help too much. Then once you have this machine learning training code, which more often than not will look like some kind of a workflow, then the next question comes is that, okay, how do I schedule this workflow? Maybe I want to train this model every single time my data set refreshes, or I want to train this model anytime I detect that my model performance is going down. So how do I schedule those? Most organizations, they have already invested in some data orchestrator. I mean, data engineering efforts usually precede any ML efforts. And as part of that, there may be workflow orchestrators like Airflow or Argo workflows or step functions, Google Cloud Composer, Prefect, Flight. Many of these may already be present in your organization. And it's usually helpful if data scientists can just ride on top of these orchestrators. But then there's an interesting question that, okay, how does our data scientists translate their work into something that these orchestrators understand? Once you have all of this, then you also have to recognize the fact that, of course, machine learning at the end of the day, it's an iterative activity. Our data scientists, they are cycling through a bunch of different hypotheses. So they want to keep a running log of all the experiments that they are doing. They want to track how models are behaving, which model is a better performing model and whatnot. Could be the case that some models that they have generated, some ancillary information, let's say, as part of their model training process, they may also generate certain kind of embeddings. And there could be other teams who may be interested in this output. How can they get access to that? Another interesting scenario is that maybe their model training workflow fails for whatever reason. Can we reproduce that failure? Do we have access to enough logs? Do we have access to enough internal state so that we can reliably reproduce that failure over and over again so that we can go ahead and fix it? This also has a nice side effect of making sure that any data scientist can reproduce any other data scientist's work. And if they want to build on top of it, they can go ahead and do that. Now, once we have a model, that model needs to be consumed somewhere. That brings us this interesting problem of how to deploy this model. You can imagine, like let's say if our user is responsible for predicting if a customer is going to churn or not, maybe that model is being consumed by a service that's being used by our customer service representatives, so that anytime you call them, they can figure out that, okay, like what is the likelihood that you'll cancel the service in the next 1 week. You can imagine that the service may not really have as much QPS as, let's say, the Netflix recommendation service. So the SLAs that govern the service may be rather loose compared to any of the recommendation related systems. But what happens if I need to deploy this model into a recommendation service, or maybe I need to deploy this model into our payment flow or our sign up flow so that we can front certain kinds of discounts to the user? Maybe all we need to do is look at this model, generate some results offline, and create a memo that lives as, let's say, just a Google Doc that gets shared with the leadership so that they can figure out interesting pricing plans to introduce in any given geography. Or maybe this model gets deployed into cell phones to guide different kinds of UIs and whatnot. Now, we still haven't sort of like focused too much on one of the most interesting components of all of this, right? Like modeling, right? Like how do you actually take this business problem of predicting customer churn and translate that into a mathematical model? And depending on the problem that you're solving, you may have access to different kinds of data sets. Maybe you're focused on an NLP problem and you have access to text data. Maybe you are responsible for figuring out like how do we do automated quality analysis of all the raw footage that gets generated. So you're working with reams and reams of video data. Maybe you have access to tabular data in the case of our customer churn prediction problem and whatnot. And depending on the problem, depending on the data that you have available, depending on what you're expecting as an output, you may want to try different modeling strategies, right? And the good thing is that our data scientists, they are expected to be subject matter experts in this particular area. Now, to reliably deliver value with machine learning, any organization, they need to be good at all of these major layers of the stack, as well as they need to deal with the interactions between these different layers well. Now, depending on who you ask, there may be different orders of concerns. For a data scientist, the thing that they may care about the most is having freedom of choice in terms of how they want to do modeling. They do care about getting fast access to data, getting reliable access to compute, making sure that they don't have to spend a lot of time creating these workflows, ensuring that there is reproducibility. But how that happens, the actual semantics of it, the actual specifics of it, they still have sort of like rather less concerns on that particular front, maybe weakly held opinions on that side of the house. But if you look at it from an infrastructure point of view, if you look at it from the point of view of a person like me who is tasked with building infrastructure, this stack is rather bottom heavy. At the top levels of the stack, I can still go out and adopt an open source training library and whatnot for most practical purposes. But then I still need to figure out what is the best way to store data. What sort of data storing tooling should I be relying on? How should I be setting up my query engines? How should I be managing my Kubernetes clusters? What sort of hardening I need to do to support many concurrent users? What kind of workflow orchestrator should I be deploying? Should my user be directly writing these workflows, or is there some other layer of abstraction that I'm providing and what? So these were the same questions that we were answering at Netflix. And as part of that, we built an open sourced this project, which is now being used by many other companies besides Netflix. So if you look at other streaming providers, financial services firms, other big tech companies, biotech firms, hedge funds, and whatnot, many other companies from all walks of life have found benefit in using this project that we started. And given that we only have 20 minutes for this talk, I'll give you a very high level overview of how we went about solving many of these problems that I just mentioned. And if this sounds interesting, we do have an open source community around the project. So I'd be happy to hear back from you in that community. So the very first thing that Metaflow enables is defining these workflows. If you look at sort of like any machine learning training code, you can articulate that as a directed acyclic graph. You are ingesting some data from some data source, you're transforming that data, maybe generating some features, training a bunch of models, maybe one model, maybe multiple models, and then you're doing something with that model, maybe picking the best model, storing it somewhere, maybe deploying that model somewhere, maybe just deploying a lot of those models, stashing them somewhere so that a further downstream process can pick those up. In this particular scenario, defining a workflow is rather straightforward. So you have this step Python decorator. So any Python function that you annotate with this decorator becomes a node in your graph. And then the last line in that method, it sort of like denotes what is the edge between different nodes. And you can very simply just execute this workflow. So you can just call Python, whatever is your file name, run, and Metaflow will execute that. To do this, all you need to do is just pip install Metaflow. You don't need to deploy any new services and whatnot. So getting started is very, very simple and straightforward. But now, once you have defined your workflow, the very first question that comes up is that, okay, how do I get some input data into this workflow? And now, one sort of like interesting observation here is that if you look at data access patterns for many of these machine learning workflows, they are usually pulling one or more partitions out of some table that's already stored in the data warehouse that forms the bulk of access patterns. And in those scenarios, in those situations, it may actually not be efficient to go through an actual query engine like Spark or Presto to get access to those data sets. You can, in many cases, just bypass these query engines, go directly to the source, maybe directly to S3, and pull those files into the user's compute environment, which is what Metaflow enables. So Metaflow ships with fast data layer. So in this particular example, you can use Metaflow's S3 client to get upwards of 25 Gbps of throughput, which can essentially ensure that every single time you're iterating on your workflow, your data goes from your data warehouse to your compute instance in a matter of seconds rather than taking minutes, which can significantly improve the quality of life when it comes to iterating on these workflows. Now, every single time you execute any workflow that's written using Metaflow, everything gets automatically versioned. Of course, we just spoke about how to get input data into your workflow, but then how do you pass state from one step to the other? That's also really important. So you can look at this example where we have this alpha as a variable that's set to zero 0.5 in the start step. And in the next step, you can very easily access the same value. And this value will be snapshotted. So you or any of your colleague can ask this question that, hey, can I get access to the value of alpha for my flows execution that happened 6 months ago? And Metaflow will provide you the value of 0.5. This could very well be a model. This could very well be embeddings that you generate that other downstream teams can depend on to consume. Now, once you have created this workflow, of course, as we discussed before, there are many compute challenges that people can quickly run into. Maybe you want to run a specific step because it processes a lot of data on an instance that has high memory, or maybe you want to run a training step on an instance that has GPUs. In this particular example, let's say maybe I want to train a model across 100 different hyperparameters. So you can very simply just specify this at resources decorator, and in this particular scenario, there will be 100 copies of the train step that will each run on an instance that has 128 gigs of RAM. And of course, we have users who are running compute that fans out to thousands and tens of thousands of tasks, which means that they have very quickly supercomputing scale compute available at their fingertips, and they don't really have to jump through very many hoops. Metaflow figures out how to take the user code and make it available in the cloud and make sure that the exact same data sets are also available and everything is snapshotted and available for consumption further downstream, whether within the workflow or outside of the workflow by other consumers. Now, here's our user. They have been able to create a workflow in a very simple and straightforward manner. They have access to high throughput input data. Everything is snapshotted and versioned. Anytime they want to get access to the compute that's available in their compute cluster, that's easy to do that. Very practically, Metaflow supports a few different flavors of compute and data storage. So today you can go out and you can use Metaflow with either of the three major public clouds, whether it's AWS, GCP, or Azure. And you can use Kubernetes as the compute platform. With AWS, we also provide integrations with managed services. So you can use AWS Batch for your compute. And then, of course, rely on S3 as your data storage layer. Once you have this workflow that you have created, that's running fine on your laptop, compute can still be offloaded into the cloud environment. What happens if you want to now schedule this compute and you want to ensure that this compute runs, let's say, every midnight or whenever sort of there's new data sets that come up. Now, one good thing is that there are a whole bunch of workflow orchestrators that are out there that are battle hardened, that provide sort of really great guarantees. It's very likely that many of the data engineers in your organization may already be using one of these workflow orchestrators. Now, these orchestrators, they also execute some form of a directed acyclic graph. So Metaflow automatically compiles down a Metaflow flow into a format that these workflow orchestrators understand. And at that point, you basically get the benefits of both the worlds, where you don't have to manage a brand new workflow orchestrator. You can piggyback on your existing investments. And your data scientists, they don't have to learn a new dialect. They don't have to interface with a brand new workflow orchestrator. So if, let's say, at any point in time, the infrastructure engineer decides that, hey, like maybe it's time to sunset Airflow and move on to Argo workflows, data scientists don't have to go back and redo their work. They still live in the Metaflow universe, and it's just, rather than executing their workflows on Airflow, now they start executing on Argo workflows, but you get the exact same benefits. And of course, anytime any workflow fails on any of these workflow orchestrators, you also, given Metaflow's versioning and snapshotting capabilities, you can reproduce those failures on your laptop and you can rerun your work. And once you have fixed your bugs, then you can push out your workflow for resuming execution on these platforms. Now, there are quite a number of other features and functionalities that Metaflow includes, which is geared towards providing a production grade and enterprise grade experience. We would want to make sure that multiple data scientists within an organization, they are able to collaborate on a given project without stepping over one another. It should be possible for me to look at my colleagues' work, fork that work, execute that workflow with the utmost confidence that I'm not going to overwrite any important information in the production database and whatnot. So Metaflow provides for high degree of isolation from that perspective, using decorators like at project. An important use case, an important question for folks is that, okay, like now the user is responsible for writing the code, the data already exists. How do we provision an execution environment? If we need to execute, or if we need to train a model using PyTorch, how do we get to PyTorch in the first place? How do we deploy that? How do we manage that? Do we bake Docker images? Do we create execution environments alongside the code and whatnot? So Metaflow provides many tools to support that as well. And then, of course, every single execution is tracked, it's versioned, there's a unique identifier that's attached to it so that people can sort of like stitch together many of these workflows one after the other. I know we are running super short on time, so I want to leave everyone with this final idea that there is a thick stack of infrastructure that needs to be provisioned in any given organization to ensure that more and more projects find their way to production. And this thick stack, this layer cake, all of these individual layers, they also interact with one another quite a bit. And from a data scientist point of view, they really enjoy any kind of freedom that can be afforded at the top layers of the stack. If you look at Metaflow is not at all opinionated about what kind of models, what kind of libraries, training frameworks a data scientist is using. But then it provides them all the affordances that they need around getting high throughput data access, running high scale compute, not having to worry about different workflow orchestrators, and getting strong notion of reproducibility out of the box. If this interests you, we have a Slack community. Please join us. I'd be looking forward to hearing your questions. Thank you.